In this video, we are going to proceed with the next series, which is Maclaurin Series. At the end of the lesson, you should be able to apply Maclaurin Series to obtain series expansions of functions. The second one is to approximate values from the Maclaurin series. So, given the Taylor series for fx about x equals to a is given by this expression. So for a special case where a is equals to 0, so when we substitute a equals to 0 into this expression, the Taylor series here becomes in terms of equation 2, where fx is equals to f naught plus x, the first derivative of f of 0 plus x squared over 2 factorial times with second derivative of function of 0 and so on. So this series is called as Maclaurin series. So to make you understand more on Maclaurin series, let's try this example. Use Maclaurin series. So they already stated that we have to use Maclaurin series to obtain the first three non-zero terms. So this is important for the following function. So the first one, we will solve sin x, and then we solve ln 1 plus 2x. So for the first question, where the function is equals to sin x, so since we have to use the Maclaurin series, meaning that our x is equals to 0. So now we substitute our x with 0. So our functions of sin x is equals to sin 0. This will be equals to 0. So the next step is the same, just like Taylor series, where we have to find the derivative of this function, which will become cos x. And then the first derivative of 0, substitute x equals to 0 into the first derivative, we have cos 0, which is equals to 1. The next step is find the second derivative and substitute x equals to 0. And then now we have our first set 2 non-zero terms. What we need to do is we have to find the first 3 non-zero terms. So we have to find another 2 derivative. So our the fourth derivative will be equals to sin x, which is equals to 0. And the fifth derivative, which is equals to cos x, okay, now we have the first 3 non-zero terms. What we need to do is we substitute our function, which is sin x, into the Maclaurin series. So our Maclaurin series is equals to f0 plus x, first derivative of 0, plus x squared over 2 factorial x cubed up until x to the power of n over n factorial times with the n derivative of 0. So we substitute the value of f naught, the first derivative, all these coefficients into this series. So our f node is equals to 0 plus x f prime, which is 1, plus x squared. This is equals to 0, x cubed, negative 1, x over 4 factorial will be equals to 0. And the last one is x to the power of 5 over 5 factorial times with f5, which is 1. So now we expand this. We will get x. So it will be 0 minus x cubed over 3 factorial. And then this will be 0 plus x5 to the power over 5 factorial. So the series of sin x using Maclaurin series is in terms of this. Now what I want you to do is pause this video and try to solve this ln 1 plus 2x using the Maclaurin series. The solution will be shown in the next slide. So you can compare the solution with your solution and check whether you got the correct answer or wrong. Now let us try another type of example. If y is equals to ln of cos x, show that the second derivative of y plus 1 plus the first derivative square is equals to 0. So the first thing is we need to show that our y fulfill this equation. Then the second one is obtain the Maclaurin series of y equals to ln cos x in the ascending power of x up to the term containing x to the power of 4. Okay, now let us solve the first questions where we have to show that d squared y over dx squared plus 1 plus the first derivative square equals to 0, given y is equals to ln of cos x. So what we need to do is we have to find this first derivative and the second derivative of y equals to this, and then substitute into the equation. So we have y equals to ln of cos x dy over dx will be equals to 1 over cos x times with the derivative of inside function, which is cos x. So we have here is equals to negative sin x over cos x, where this can be represented as tangent x. So we have negative of tangent x. The second derivative of tangent x is equals to the derivative of negative of tangent x, which is equals to negative of secant square x. Now we have solved the first and the second derivative. Next is substitute into the equation. So the equation we have here is the second derivative plus 1 so our second derivative is equals to negative secant square x plus 1 plus dy over dx, which is negative tangent x square. So here we have negative secant square x plus 1 plus tangent square x. So 1 plus tangent square x can be represented as secant square x. So here we have negative secant square x plus this we get equals to 0. So it is shown that y y completes this equation. Next is we have to obtain the Maclaurin series of y equals to ln cos x. So what we have here is we can represent our function of y in terms of fx, which is equals to ln cos of x. So our f naught is equals to ln cos 0, which is equals to ln 1. So this is equals to 0. And then our dy over dx, which is equals to f prime x, is equals to negative tangent x, where we have found the dy dx of this ln cos x from the previous question. So we just take the dy dx into this, and our next step is to find the derivative, the x equals to 0 into the function of the first derivative. So negative tangent 0, which is equals to 0. And then the second derivative is equals to, this is equals to negative secant square x. So the second derivative of 0 is equals to this, which is equals to 1. And then we proceed with the finding the third derivative. So this one we have to calculate by ourselves. So here will be negative 2 secant square x tangent x. And then substitute x equals to 0. So we have negative 2 times with secant square 0 tangent 0, which is equals to 0. And the last one is the fourth derivative. So in order to find the derivative of this function, what we need to use is the product rule. So you can try this, and the final answer should be in terms of this form. So our fourth derivative when x equals to 0 is equals to negative 2. So why I have to find until the fourth derivative? Because the question asks you to get the ascending power of x up to the term containing x to the power of 4. So in order to find the term containing x to the power of 4, you have to find the fourth derivative from the function. So from this function, all this value, we substitute into the Maclaurin series, where Maclaurin series, here we have is equals to f naught plus x f prime plus x squared over 2 times with second derivative plus x cubed and the last one is plus x to the power of 4 over 4 factorial times with the fourth derivative of 0. substitute all the value where we have f naught is equals to 0, our f first derivative is equals to 0, our second derivative is equals to -1, plus the third derivative is equals to 0, and the last one plus x to the power of 4 times with -2. So simplifying this, we get 0, 0, negative x squared over 2 factorial. Here will be 0, and this one will be 2x over 4 factorial. So that is the expansion of ln cos of x.